All right. Hello, everyone. Let me fix my iPad settings before I forget. Okay. So I am gonna assume sound is good, video is good. If something isn't working, please write about this in chat. Mic seems to be working. Wait, is this right? I think this is right. Okay. So today we are going to talk about, or mostly not talk, but today we are going to write a bunch of code. And that is going to be code related to optimizing whatever we have been writing on previous streams and maybe cleaning this up a little bit. So for people who haven't watched the previous streams or don't remember, where we have landed so far is that compared to like the state where we were who knows how many months ago. So we've implemented triangle culling in the mesh shader, and we've implemented occlusion culling for meshlets in the task shader. The problem that we ran into on the last stream, or there is like sort of two problems here. One we didn't talk about because we didn't really have time to talk about this. One problem we kind of ended up with on the last stream was that it became really difficult to like reason about the code that we have written. I said something to the effect that I think the code is correct, but it's really hard to actually convince yourself of the fact that it is correct. And it's because of this two-pass structure that with the introduction of occlusion culling for individual meshlets, the two-pass structure for occlusion culling got difficult to reason about because it's actually sort of 2.5 or 3 pass sort of thing. And like now sometimes objects get rendered in both passes and it's complicated. Some of this complexity is inevitable. Some of this complexity is an artifact of how we have implemented the culling. The other thing is that we didn't discuss this on stream, but when I checked the timings after the stream ended, it looks like the occlusion culling reduces number of triangles substantially, but it actually also reduces performance, which is not a happy place to be. You would like to be, you would like your culling solution to sort of improve performance, not reduce performance. And part of the reason I suspect for this is the thing we did discuss on stream, which is that to implement this two-pass, two-phase culling, we needed a state for each meshlet that we render on screen, which is a new thing. We didn't used to do that before. And we were trying to get things to work, so we just allocated like 32 bits or like 4 bytes for every meshlet, and it's a lot of memory. It's 1.2 gigabytes of memory. We aren't using that entire buffer, but it is likely that accessing this buffer is part of why things are kind of slow, because it's a very large buffer that we access very few sort of useful bits out of. We aren't currently using a graphics profiler, so it's hard to like confirm or deny this. But in general on stream today, I want to get through a few things, a few items that try to either optimize things, as in get things to render faster, or clean it up, as in maybe there's no performance difference, but the result is easier to reason about or somehow beneficial for us in some way, now or in the future. So that is what the goal is today. I have this list of things that we may or may not get through all of them. Maybe we only get through half, and this is fine. Then there's going to be one more stream. And we will just sort of start doing this. There is the thing we have to start with, which I don't want to belabor too much because Because, how do I put this? We are gonna profile performance on stream today, as in we are gonna look at timings. We're not gonna use a profiler yet. There was a question in chat which is, will we use a profiler? And I think it's a good idea to use a profiler. The only reason why, honestly, we won't do this right now is there's a profiler for AMD GPUs which is called RGP. I haven't checked if it works with the graphics driver that we're using. If it doesn't, or if there's some issues, like I'd rather figure out stuff like this off stream. So I just don't want to like get into that right now, right? But we definitely should explore profiling with an actual profiler. It just won't be this stream because there's a lot of obvious, there's like, I don't like where we ended, I don't like the code that we ended up with last stream, right? So like I'd rather first fix the code so that I actually like it and then actually use the profiler to figure out if the code is good or not. If it doesn't work with the Radar driver, then we'd have to wait for the support for mesh shaders for the other AMD driver in Linux, and that has not happened yet, I believe. Let's check. I believe that hasn't happened yet. Yeah, so this was updated last year with, there was an update, like we can build the other AMD driver from source. I just don't want to. It's likely that I haven't tried. Maybe it's easy, but it might be more complicated than building the one that I'm using right now. Anyway, So this is where we ended with last time. We have occlusion culling implemented. We are rendering 3.5 million triangles, which is actually not a lot because before occlusion culling we were rendering 6.6 or something. We take a bunch of time to do this, or it's hard to tell, right? So like 9 milliseconds, is it good or is it bad? It's worth noting that 3.5 million is the number that gets fed to the rasterizer. The number that we are feeding into our overall pipeline is much larger. If we disable all stages of culling, I think it's 1 billion triangles or so, I forget. I did some numbers for the recent blog post that I wrote. So it's hard to know if this is a good number or a bad number, right? If we disable, there was this curious thing that I remarked upon on last stream, which I haven't traced to any specific issue. If we go through the traditional rasterization pipeline, we take 20 milliseconds to render the same scene, which is much larger than we do with meshlets. When I was testing this before, like 3 weeks ago, it wasn't 20, it was more like 7. So it looks as if but triangle culling does work. So like, I don't know what happened. Something weird happened with the performance of the traditional rasterization pipeline, even though we haven't changed much, I think. Like, but whatever, it's not going to be the focus right now. Ideally, we would get the traditional pipeline in shape as well, but I want to first resolve the inefficiencies in the newer pipeline and then look at the original one. So I don't know if it's the case that some driver configuration changed, or if it's the case that we have changed the code somehow to break it performance-wise. I don't know what crime we could have committed from the performance perspective, because the number of triangles is correct. Number of triangles is 6.7 million, so we aren't rendering redundant triangles. We know that. One thing I haven't checked. Maybe this is what changed. This would explain a bunch of things. Let's, in theory, okay. In theory, it shouldn't matter which configuration we build things in, because in debug we enable validation layers, but that should be just CPU overhead. Oh yeah, this was totally it. Okay. So this is what changed. In debug, for some reason, only with the traditional rasterization pipeline, there's a substantial amount of overhead somehow on the GPU. All right, we will not, let's just keep it this way. We are going to work without validation layers, which is probably fine. Or It's fine for now. All right, so now it's easier to talk about this stuff. So we have this new pipeline with meshlets, etc., in a good conceptual state, as in it's culling a lot of triangles, etc., but it's still slower than the traditional one. If we disable meshlets, we render at something like 7 milliseconds, and if we enable mesh shading, then we render at something like 9. So let's fix all of that. Well, let's try to fix all of that to the extent that we can. So the first thing I wanna fix is the configuration of the mesh shader with respect to how many triangles and vertices, etc., we use per meshlet. I don't want to discuss this point too much because I don't have the right answers yet. There is a bunch of stuff that isn't fully baked in this whole. There's some questions about the number of like there's different ways to configure the AMD mesh shading hardware on the GPU that we have. The driver supports one of them right now, and it doesn't fully support the other one, although I tried. There's like a way to force it to use 32, the waves of size 32, and it changes a few things. And then newer GPUs of AMD, like RDNA 3 GPUs that shipped this year, last year, right? They support a few key hardware optimizations, but these are not reflected in the driver that I use yet. And also I don't have an RDNA 3 GPU yet. So ideally we'd have a detailed discussion about this entire problem at a later date, right? For now, I'm just gonna do a couple of things sort of blindly like I did them before. I know they get us to a much better place. I don't want to spend a lot of time experimenting with this or discussing this because this is likely not the actual optimal solution, but it's going to get us to a slightly better place. It's going to get us to a better baseline. Like I don't want to benchmark things in the state where I know we are not utilizing the mesh shading hardware well. The upshot of this, like what we have to do is just reduce the number of vertices and primitives to be equal and to be divisible by 64, which means 64 or 128. I want to go with 64 for now. This is the config I tested before. It's okay. It's not great for, like I suspect this is going to lose performance on NVIDIA compared to the current configuration that we use. But there is this general problem of optimizing mesh shaders on all architectures at once. Which is a hard problem, which, again, I don't think we are quite ready for sort of discussing this. I also just got an Intel Arc GPU that also should support mesh shading, and so it is likely that on the next stream we'll actually try to see what performance is like with mesh shading on that GPU, if it works. And so there's going to be a better time to do this. Anyway, so this is the first sort of big change. We need to change the meshlet configuration. There's another change that I need to make, but I think this is good to start with. Okay, this is still 9 milliseconds, but this is fine. Maybe not much is changing there. The other thing is there is this loop. So again, I'm not talking about this stuff in detail. Let's actually copy this comment because there's gonna be another stream at some point where we talk about why these things are important on AMD hardware and what do you do on other GPUs that are not AMD, where these things are unimportant and in fact may be hurtful. Okay, so we changed both of these things. We're still rendering at 9 milliseconds per frame, but this is fine. One experiment we can do now is this. So we spent all this time last stream implementing occlusion culling. The question is what happens if, occlusion culling for meshlets specifically. The question is, are we gaining time or are we losing time on doing that work? I talked about this on all previous streams. When you implement an additional culling optimization, it's vital to make sure that you are spending less time on doing these computations than the amount of time that you're saving as a result of this extra work, right? So, and this code is messy now. Like I mentioned, that this is a problem which we are going to try to address. By the way, I have to be really careful now. Any mistake that you make in this code may force us to like reboot the system basically. I haven't figured out. There's very limited amount of support again. Like it feels like either there's no great support for restarting the driver, or I just don't know what magic commands to type. Like whenever I get myself in a situation where there is a problem in the shaders that results in some data corruption on the GPU, I have crazy screen corruption artifacts, and then I can't really recover from them. Like I have to reboot the whole thing. So we're gonna try to be careful and not get ourselves in a state where we'll have to restart the stream. I think this is how you disable. So we aren't touching this giant 1.2 gigabyte buffer anymore. Okay, so we disabled essentially all of the work that we did last stream, more or less. And what this got us with this new, better configuration of mesh shaders, which again I don't want to talk about right now, is that we are rendering at 7 milliseconds, give or take. So it's similar performance to the traditional pipeline. Whereas when we add occlusion culling, we drop the number of triangles by half, which is really good, but also we increase the amount of time we take to render by like 1 millisecond or so, right? Or by 2 milliseconds or so, so 7 to 9. So this means that we are not very... like our occlusion culling is inefficient, not as in it works bad, like it works really well, but it takes a lot of time to do this. And so we're gonna try to fix this. By the way, when I adjusted these configuration parameters just now for the meshlets, I increased the effective total number of meshlets by what looks like 1.5x. So it's a substantial problem. Like I had to do this. We can try to undo this after we implement all of the optimizations, but I think I have to do this for AMD hardware to work well in this configuration. But it's not great that I have to do this because clearly it penalizes. Like rendering more meshlets is worse than not having to do so, right? So clearly there is sort of some problems for us to resolve around all of this. Anyway, all right, so let me check if I want to commit this simple change that essentially changes the configuration to be more optimal for AMD. And then I want to actually start working on occlusion culling stuff. This is day 19. What ideally has to happen around all of these limits is that some of these can be... I'd like to land in a spot where there's a fixed meshlet configuration, but variable mesh shader configuration, because that allows us to build meshlet data offline and then have like a couple different shader variants for different vendors. Again, this requires more experimentation and stuff. Anyway, all right, so the place where we are at now is that we are taking 9 milliseconds or so to render things, and around 2 of these are spent on introducing the occlusion culling for clusters, which is not great. The big problem that I know of is this thing that I talked about where we have this giant buffer. It's actually, it was 1.2 gigabytes and now it's 1.6 gigabytes, where we store past status of meshlets, as in was a meshlet visible last frame. I talked about this on stream last time. It's important to the culling scheme that we have implemented, or rather to how we have implemented it. So I have two ideas on how to, it's a problem that we have to use this giant buffer, 1.6 gigabytes. It's a lot of memory, but also it's a lot of bandwidth, and it's all sort of, the access to this is very sparse, so it's likely that we are burning a lot of time on this. So the first observation that is easy, and I have two possible variants I want to try, or sort of three, depending on how you look at this. So the first observation that's very easy is this. We've allocated 32 bits for every meshlet, but really we only need one bit. We need to store a boolean that says on the last frame, was this cluster or meshlet, the terms are used interchangeably, visible or not? And then there's different logic that we use based on whether it was visible or not. So one option, we can easily just drop this to 1 byte, but it's still a lot of data. Like right now it's 1.6 gigabytes, so it would be 400 megabytes. It's still a ton of memory to store visibility state. So the first idea is, well, we only need 1 bit. So let's just use a bit array instead of a 32-bit integer array, right? This should be reasonably easy. So we need to allocate less memory for this buffer. And then when we read from this buffer, we need to read a bit instead of reading the element of the array, right? Which is just like easy bit math. The one thing that is complicated sort of about this is that when we write, so every frame we update the visibility status with the value that's going to be used on the next frame. And right now we just do this by writing to this buffer. Well, when we have just 1 bit to write to the buffer, how do we do this? Especially given the fact that there is other threads in the GPU that concurrently access the same array, right? When we work on 4-byte units at a time, it's easy because you just write 4 bytes and you know that if other bytes in this array are being written by other threads, there's no race condition. When you write bits, there's a race condition. And so what we have to do is instead we have to use atomics. Essentially, if the cluster is visible, then we need to set the bits. So we need to do OR operation. And then if the cluster is invisible, we have to write 0. So we have to end with like an inverted mask, but we have to do all of these operations atomically. So the first idea is essentially to do that. So let's try to do this and see what happens, right? This, at the minimum, it should reduce the amount of memory that we use by like a lot, which already makes the situation less catastrophic. Yeah, I had, okay, I'll think about the second idea that I had. So I had 3 ideas. The first one is this. The second one I'm slightly less sure of now, but okay, let's do this. Let's do the first one first. So at the minimum, it's going to reduce the amount of memory that we have to use for this data. At best, it's also gonna make the rendering more efficient because you access a much smaller amount of memory for this data. But it's hard to know. So previously we said we have these many total meshlets in the scene, and that's used 4 bytes for each one. Now we are saying, well, actually, this is the number of bits that we need. So to compute the number of bytes, we have to actually divide it by 32. But if the number isn't divisible evenly, then we have to add, allocate enough data sort of for all of the bits to fit. So this is how many bytes we need to use. Now there's somewhere else. Let me use Meshlet visibility bits. I mean, okay. Bytes. So let's compute this here. It's a little awkward. Okay, whatever. And then there's one other place on the CPU where we clear this buffer first time. Let's do that. There might be alignment restrictions on these sizes. Like it might be impossible for us to create like this whole thing might have to be aligned by like 4 or 16 or something like this. Let's ignore this for a second because I think we're going to be fine for now. So let's just keep it as is. So now that we only allocate 1 bit, I think this is the only shader where we use this, yeah. So now that we only allocate 1 bit, we need to actually read the bit. So to do that, instead of accessing, instead of using this like single index as a array index, we need to divide it by 32, and then we need to end it with it should be like this. So we are reading a 32-bit value out of the visibility buffer, and then we kind of index the we read only 1 bit out of this 32-bit value, which corresponds to the last 5 bits of the global index. And then instead of using, and then one caveat is this value is not 0, 1 now, it's either 0 or 2 to the power of something that corresponds to the 1 bit that is set. So here we can't say equals to 1, we have to say not equal to 0. So then when we update this, this is the thing I was talking about, where what we want to say is if it's visible, then set the bit. 31. Otherwise, make sure that the bit is not set. So this is roughly the code that we want to write. If we just do this, then there's going to be a problem where different threads of the GPU access this array concurrently, and it's not a good time. As in, there's going to be data that's going to be corrupted. So instead, we need to use atomics. I suspect it's just atomic or I've never done this before, so I don't know if this works, but I suspect it's just atomic or here and atomic and here. Now, the efficiency of this construct is up for debate. There's a lot of threads that access a bunch of stuff with atomics. Is it fast? Is it not fast? Who knows? As I mentioned, I had a second idea that may or may not be valid that I will, I need to think a little bit about, but let's try this like this and see what happens. And maybe things are fast and maybe things are slow. Maybe things don't work. Okay, so things do not work. The time is fairly bad, 14 milliseconds, but also the culling doesn't work anymore because we are rendering 7.6 million triangles now. So we made a mistake somewhere. The question being where. So we take the index, MVI 31. The order of the arguments is correct. I don't think there's a sign issue just in case we can attempt to do this. I think 31 is correct. Yeah, this should all be correct. Are we not allocating enough memory? That seems dubious. Let's try to do this. Interesting. Huh? Whoa, what? So now culling works. 3.2 million. Why did I have... That makes no sense at all. Oh, this is not the byte count, of course. Oops. This is the... This was the number of 32-bit integers that we need, not the number of bytes, so we need to multiply it by 4. Okay. So the good news is culling works still. The bad news is it's still slow. It's not, maybe it's a tiny bit faster than it used to be, but it's still pretty slow. So the good news is we did optimize the amount of memory that we need to use pretty substantially. We can print size in megabytes. So we now use 54 megabytes for this data, which is still a fair bit, but it is much smaller than what we used to do, which is like 1.4 gigabytes. So we did optimize memory. However, from the CPU perspective, it still looks like the culling takes, the work that we need to do to make culling work takes a substantial amount of time compared to like not doing that. Okay, so then I had the second idea, which is a variant of this idea. So now I don't know if this is very useful, but it was a cool idea that I wanted to try, but let me think if it actually will work. Now, there's a problem with the second idea that I had with the way things are implemented right now. And I don't want to change the global structure of the implementation quite yet. The idea that I had was this. So we are now using 1 bit per cluster, which is sort of good, right? But actually it's still really bad. Consider this. So we are allocating data for, what is it? 450,000 meshlets. That is, so we use around 64 triangles per meshlet now. So that is around 28 billion with a B triangles, like approximately. We aren't, if you disable occlusion culling, we are not rendering anywhere near this number. We are rendering like a much smaller number of triangles. And even if you disable all culling stages, as I mentioned, I think if you disable the triangle culling, 1 billion is with level of detail. What was the number when you disable? I guess we can just do, so if you disable occlusion culling, we render 9. And then we need to disable triangle culling that we do in the mesh shader, which there's not like a button for. 23, oh no, without occlusion, 116. So we are, if you disable per triangle culling and disable occlusion culling, you end up with a number of triangles or clusters that are fed into the occlusion culling sort of workload, right? And that is 116 million triangles. And so that is around 2 million clusters. But we are allocating data for 400 million. This is because our allocation is worst case. We assume that we assume two things. One is that every single cluster of every single mesh is going to be visible on screen. And the second one is that that the level of detail selection is always going to choose the first level of detail. So neither of this is true. So we are over allocating by a lot. We are over allocating by 200x. Now, from the memory consumption perspective, this is a problem. But it is hard to say, like maybe there is some weird configuration of, we can disable level of detail, for example, with the button, right? And then we actually will use a value that's closer to this number. So maybe we always need this much memory. But the other thing is that the access to this thing is very sparse, and it doesn't necessarily have to be. So the idea that I had was to use a hash function to build an index of like the meshlet inside of this array that's much smaller, and then you can vary the number of hash buckets. The downside is that you can get false positives, and so I thought that false positives aren't good enough, or sorry, aren't like a problem, because I thought that there's going to be like I thought there's going to be a specific property that this code has, which it doesn't, because the only reason why this code works is that every bit of this data is read in a given thread, and it's written in that same thread after it's been read. And so there's no chance of this value overwriting another bit that is referenced by another thread. If we start using the hash function, we lose this property. And as a result, this value becomes somewhat random. And I believe this means, that the correctness of the calling may be impacted. Okay, so I think this is the best we can do sort of naively. It might be worth noting that this code can be implemented much better if we assume certain things are true. For example, we know that this shader is executing with 64 work groups, 64 threads in a work group. If we know that the index of the meshlet is, there is this task offset guy, which I don't remember how it's computed. LOD meshlet offset. Result meshlet size. So there is a possibility that if we align, essentially, so like sometimes, let's try this. I think this is interesting. Because of the performance numbers here, I'm hoping that the other idea that I had is going to be both nicer and faster, but I want to try out one thing that I don't think we will commit, because it tends to be flimsy is the word. So I don't know that I like this other idea, but I think this code is unambiguously better than the code we used to have. As in, it doesn't run slower, it runs at roughly the same speed, it's slightly faster, I think. And it saves us a lot of memory. So this is a clear improvement. It still doesn't make occlusion culling for individual meshlets worth it, but it's a clear improvement. And I will do more commits than I usually do, because I am scared of breaking something. And again, mistakes in this code sometimes crash the GPU, and I want to avoid this. So I will do more commits than usual. Visibility use 1. This requires us to use atomics to update this data from task shader. So here's the thought. If we think about how the GPU works with the how the GPU schedules all of these workloads. What happens is that this function ends up being run once per thread, but these threads are organized in thread groups, And the size of the thread group is 64 threads, which is this value, which happens to be 64. 64 is a good number for AMD hardware because up until recently, up until I think RDNA 2, AMD only supported 64 from the hardware perspective. Now they support 32, but we use 64 right now. Now, this means what actually happens broadly in this code is that this code gets run 64 times, and these indices, this is the oh, this is even better. We only need to align the offset. Okay, cool. Yeah. So there is this value that we've computed last stream, which is the offset into this giant buffer of visibility structures, of visibility bits, that corresponds to sort of where the bits are placed. And in every invocation of this function, the index is sort of incrementally adjusted for different threads, as in there's a work group that runs 64 threads, and the first thread in this work group has an index of like 0, and the last one has an index of 63. So they are sequential. Which means that what happens here is that actually we have 64 things that we do, 64 like values that we set. When the valid boolean is set to false, like there's problems with this value, but we do this code 64 times with incrementally increasing indices. So technically we write 64 bits here at once, where we first write the first 32 bits and then the second 32 bits. We don't know what the driver does with this code, but it feels unlikely that the driver does something very intelligent with this code, because it's hard for the driver to reason about this in this specific case, the way things are like constructed. And so it's very possible that the actual hardware sort of, like, it's possible that this code is running relatively slowly. We aren't using a profiler, so it's hard for us to check, but it's possible that it's running slowly compared to what it could have run at if we knew that, if we used the fact that these bits are updated in groups of 64 at a time. So let's try this. My best guess is that it will not change anything from the performance perspective, but I am curious to try this anyway, because maybe it does change things. And if it does change things, it would be nice. The issue with this code is going to be difficult to commit, because I'm going to write this code assuming that the hardware actually schedules things in groups of 64, which doesn't have to be true. And when it is not true, this code will break. So I don't know if... Oh, there's a way to write this code in a more cross-platform way that might use... Hold on, let me think about this. So let's say I have... Let's try this. It's going to be interesting. Let's try... I'm going to try to write this code without using the thing I was thinking of. Okay, so the first thing I want is I want the property that this index always starts with an offset that is evenly divisible by 32 or by 64. Let's just align it by 64. So when we add the count to the like running offset that we are keeping track of, we are gonna align this to the 64 boundary, which will mean that for every mesh, it's worse because we are doing meshlets. Oh, we are doing the maximum. This whole thing is a mess. How does this all work? Hold on. What? How do we compute the index again? MGI. Global invocation. Yeah, okay, this is fine. Okay, so now the start indices are aligned to the boundary of 64. This means that I keep blanking on this. Is this the magic value that is like computed by multiplying? Yeah, okay, derived. So it's workgroup ID times workgroup size plus. Okay, cool. All right. So now, okay. So when we take this thing and divide it by 32 to compute the bit index, now this thing is evenly divisible by 32, and this guy divided by 32 provides us like the extra offset. Essentially, we can decompose this value. Let's try to refactor this, not refactor, but let's try to change this a tiny bit. So actually, maybe let's leave it as is, because so what I want is essentially this MGI. Okay, yeah, so this MGI is the problem. Is instead of using this value, which is this magical value, we are going to use, so none of the code that we are writing is going to be committed, I'm pretty certain, because it's just not going to be portable across, like, it's not going to be portable. So this is the actual computation that happens. We take this offset, which is divisible by 64, and then we add the number of workgroup. Each workgroup processes 64 clusters. This thing is also divisible by 64, right? And then we add this guy, which is from 0 to 63 inclusive. So essentially, when we just look at this component of the value, this denotes the offset that points to these to the 64 bits of data that are aligned to 32 bits, or to 64 bits in this case, that are actually addressing the value. So I don't know how to call it. Let's call it this. So if we, the upshot of this is, if we do this, just take this component and then divide it by 32, then this value points to the offset in this buffer, and the only two values from this buffer, two 32-bit values from this buffer that we are going to use in this entire work group is this value and the next one after this in the buffer. Why is this useful? Why is this a useful observation? Well, the reason why this is useful is that we can compute, we can update the buffer in this location without using global atomics. How do we do this? So first, let's try to use the cross-platform sort of way. Oh my God. Okay. This whole thing is awkward because we are processing data in groups of 64-bit, but we are writing things in groups of 32-bit. But and I'm gonna be trying to rely on some magic driver optimizations, which might not be a good idea. But let's start with that. So let's add two 32-bit integer values that are located in shared memory. And then instead of saying, oh, we are gonna OR this like value that is stored in global memory with this visibility status, let's instead do the same thing, but on the shared variable. So the way we're gonna do this is we're gonna set these guys to 0. Then we're gonna make sure that all threads wait until they see both values written at 0. Technically, you only need to do this in like the first thread, but it's probably fine to do this in all threads. I'm not sure. It's probably fine. Maybe not. Okay, let's just do if gl local. I can never remember these T stands for thread. So in the first thread, we're gonna write both to 0, then we're gonna wait. We only need to do all of this when we are in a late pass. So maybe let's do this. So now, this is where these things get awkward, because we need to update one of these two depending on which thread we are in, which is just terrible. I don't know if we can use 64-bit integers, like something, like there's going to be bad consequences if we try because of reasons. So let's do this. Technically, it doesn't matter which thing we are ending. Well, it does. Hold on. So, okay. If we are, so there's going to be 64 threads that are processing this thing. If we are in the first group of threads, then we are going to update visibility 0. Otherwise, we're going to be updating visibility 1. Oh, but this clearly doesn't. Oh, this is better even. Oh, this is cool. Hold on. So now that we aren't contending against writes in other threads, we can just say only if the cluster is valid and visible, we are gonna update. Cool. Okay. We had this code before that set the bit to 0, but if we are setting bits in groups of 64 that are aligned, we can just set them all to 0 first and then like write them. It was difficult for us to do that before because we weren't like there could be threads that are not in our work group that would be writing to these values and stuff like this, but now none of this is like a problem. So if it's valid and visible, then we are setting the bit into one of the two shared variables. Then we will wait for all of the updates to all of the variables to happen. And then only in the first thread, and you can technically do this across more than one thread, but only in the first thread, we're going to actually write these values to the global memory. So this is this MVI64 that I strategically stashed. One and 2. So I think this code works. Who knows? Let's try to run it. Let's hope nothing crashes. But so the broad idea here is that once we are processing things in groups of 64, which we always were, but now that we can take advantage of this fact, instead of updating for every cluster some bit in some global memory somewhere, we're saying let's aggregate the 64 bits of visibility for 64 meshlets that we are processing right now into these two 32-bit variables in local storage, in per thread group storage. And then once we are done, write it all to memory. Let's see if this works. Hey, this works. This is not faster. In fact, it runs at around the same speed, but at least it does work. Now the caveat with how did this suddenly become 61? Oh, it's because I'm aligning everything so there's more memory. So now the thing I wanted to try here specifically wasn't this. But as I was saying, none of this code seems to actually be improving performance, and none of this code is probably a good idea. But the reason I wanted to try all of this is it's another excuse to use Ballot, which is a cool primitive that is very hard to use correctly, which is why we're not going to commit any of this code. But so we don't know what the driver does with this code. Under certain conditions, the driver can take code like this and compile it to something really optimal. However, this doesn't always work. We can check if the driver does this, but again, we're going to be like reverting all of this code. So I think we should just do so I think we are just gonna sort of see what happens if we use Ballot, and then none of this will change performance, and then we'll revert all of this, and then we'll try to implement the second thing that I was thinking of, or the third thing that I was thinking of. So this, we actually used Ballot like many years ago when we started this series. On some stream we actually used Ballot already, so I don't want to go into how Ballot works, especially because it's already been 50 minutes and we still haven't really improved performance, which is a little bit of a shame. So just refer back to a stream if you want to learn more. But basically, this code looks a little bit magical now because there is like not much of it left. But what it does is it essentially allows us a way to get the value of this expression in all of the 64 threads and then convert it to a single value. Do I have to do it outside of the control flow inside of the... So this control flow is uniform, so that should be fine. Yeah, I have to use it outside, of course, and then, yeah, okay. Broadcast first. Is there a better way that we should be using to check if... No, I think this is correct. It's gonna ask us for an extension. Oh, it's not gonna ask us for an extension. Okay. The code works. It's hard to reason about the performance of this code because there is clock variation and stuff like this. This code runs at 8.92 milliseconds. Without Ballot, it also basically ran at 8.92. Okay, yeah. So either this code isn't actually on the critical path or the driver does the Ballot optimization regardless. So all of this is cool and all. It doesn't actually make things better, as in, if we stop doing all of this, then we are running, well, this actually did help. Now that I run without these optimizations, no, it didn't help. See, this is, the variance in the timing is substantial, and so it's hard to ascertain like either we're making things better or worse if we are doing them in very small increments. But okay, so we were running at 8.91 before this, before we tried this, and then at 8.92 after we tried this. So Ballot was a bad idea. Let's forget that any of this happened. I just wanted to try this Ballot thing. Okay, so where we are right now is that we are still taking the extra 2 milliseconds or whatever to do occlusion culling. As in, disabling occlusion culling makes things faster by around 2 milliseconds. Oh, disable occlusion culling for clusters specifically. So there is various reasons for why this might be true, and it's hard to know which one applies. The other thing that's difficult about this code is that I'm now starting to think that maybe the third thing that I wanted to try also won't help, which would be a shame because the third thing is more difficult to try than the thing we tried just now. Let me think about this for a second. I think the good news is we are not using a lot of memory now, or as much memory for the occlusion culling. So the bad news is we still need a way to make occlusion culling worth it for clusters. Oh, right. One thing I think we tried on last stream, but maybe we didn't. There is a way to measure the, how do I put this? When you think about the occlusion culling for meshlets that we did last time, there's two places where the overhead comes from, or can come from. One is the actual occlusion check. This is that. It's us fetching data from the depth pyramid, comparing depth, etc. The other one is the infrastructure. The infrastructure comes again in two places. One is that we need to work with this like visibility bits, which is the code that we just changed, right? Like, so read this data, write this data. Now we use atomics to write this data, etc. And then the other one is that at the higher level, when we do draw call culling, before we had two passes, early and late, and we only rendered an object once. It either goes into the early pass or it goes into the late pass. Now we have to render some number of objects in the late pass and in the early pass. But we aren't just rendering them twice, we are only rendering parts of the object in the early pass and parts of them in the late pass. So we are submitting the whole object twice, in the early and the late pass, and then we use the cluster culling to cull parts in one pass and parts in other pass, right? So there's sort of three places, right? With the actual occlusion test, the mechanics in the task shader that have to do with fetching these bits and updating these bits and all of that, and the actual and the high level sort of this distinction between early and late passes. In all of these three places, we are introducing overhead. In the actual test, occlusion test, takes some time. The extra manipulations with bits and whatever take some time. The fact that we have to submit an object again takes some time. It would be useful to get a rough sense of where our performance problem, where this extra overhead lies primarily. Because if the core issue is the fact that we dispatch the object twice now instead of just once, if that's the problem, then it's going to be very hard to address this problem because it's kind of the fundamentals of the technique. The technique demands that this has to happen. If the problem has to do with the other two parts of the overhead, then there is various ways of implementing this in different sort of places, and like there's ways around this. So I kind of want to know broadly. So I said we are spending 2 extra milliseconds on this stuff. But why? Like, where is this coming from? The issue that makes it difficult to isolate the overhead is that all of these three parts are connected. There is this single algorithm that has 3 things that are required for the algorithm to work. You have to render the object twice and then call parts of this in 2 different passes. You have to preserve the visibility status across frames. We discussed this last time. It's finicky. It has to work in a very precise manner. And for the actual occlusion to work, you have to do the actual occlusion test, right? So all of these 3 things are required to make things work. However, one thing we can do, for example, is we can say, well, what happens if we never run the actual occlusion code? So like if we just disable this visibility update, we are still updating all of the bits. So that code still has to run, and it has to run the exact same way as it did before. And we still have this higher level dispatch. So let's see what happens. What happens is you have to use it false, I guess. All right. So this is interesting. So if we are not, this is getting us useful information. Let's start writing down like a few numbers, because I think this stuff is it's gonna help us think through this problem. So I was already saying why I don't want to use RGB right now. I think right now the how do I put this? So there's some parts of this that are like RGB would be useful, but RGB would take time to set up, and I don't know if it would work, right? So I don't want to do this right now. Yeah. So there's a way to okay, there's a way to output assembly. So this is good to know. Thank you. I used like a Vulkan extension to do this before, which required a bunch of setup, so I didn't want to do it on stream right now. But if there's a command line variable, it's easier to do. However, I think our real issue is probably higher level, so I want to look at a little bit at some high level metrics. But yeah, RGB would make some things easier. It's just, Tracy wouldn't help, right? So Tracy doesn't have visibility into the hardware. It can only work on the level of the Vulkan timers, which we already use Vulkan timers. We aren't currently timing the early pass versus the late pass separately, or actually we are. We're just adding up the timers together for display. So that we already do. Like Tracy doesn't bias much. RGB would bias something, because RGB potentially would give us information about specific time, sort of specific amount of time spent in specific stages, etc. I don't know if RGB even works with mesh shaders and stuff like this. Like my guess would be no, it's all very early. If it does, then that's great. I just don't wanna figure out that it doesn't work after spending a bunch of time setting this up. Like I just suspect RGB in this specific case isn't gonna help us yet, because it probably doesn't have support for this. We aren't using official driver, etc. Anyway, so let's write some numbers down. I'm gonna split early and late pass actually, because yeah, this is it wasn't very important before, but it's becoming important. But okay, hold on. So we have 8.92 milliseconds per frame is the number that we call, and we did bit array. So let's mark this down. So we are using 8.92 milliseconds. This is when we have full occlusion culling, right? So let's again perform the experiment where we disable all of this garbage. Do we still have? No, okay, cool. And then there's a lot of variance in this. I wanted to update the this is the area where, like, if we use Tracy, it would help us a little bit, because it would do a better job of showing us like the histogram of numbers and stuff like this. But let's just say that it takes us around 7 milliseconds, give or take, without occlusion culling off and then occlusion culling on. So then it's interesting that what happens so now, hold on, let me so if we don't do the actual occlusion tests for meshlets, but we do all of the rest of the work, then I think it was 10.4, yeah. So then we have 10.4 milliseconds this is sort of occlusion kind of on without the actual test, right? So we don't do the sampling from the depth buffer, which disables the effects of the occlusion culling. So all of, like, everything that's left is pure overhead, right? So we increase the amount of time by doing that from 8.92 to 10.4, which is 1.5, so 1.5 milliseconds. So I think what this means is essentially this: the actual test itself is pure win, as in, by doing this test, however much time it takes us to actually sample this occlusion buffer, it removes 1.5 milliseconds in aggregate when you include this overhead from the later stages. So like, the actual test is working and it's a good idea. However, the total overhead of doing this whole operation is very large, right? We are going from 7 to 10.4. There's two places, now that we don't even run this code, there's two places where this overhead comes from. One is the operations with the visibility bits, and the other one is the high-level restructuring. Now the issue is, I was saying how these two things are, how all of these three stages are connected, in the sense that it's hard to disable one without the other. When we disable this one, things still should work. If I can't disable this, because if I disable this and this alone, then we are gonna start rendering more triangles, I think. So I think what I have to do, let me think. If I only disable this, I'm not sure if things will work or not. Let's try. This whole thing is delicate. Yeah, I think this works correctly. Yeah, and we are back to basically 7 milliseconds. Yeah, okay. So this is unfortunate. Okay, I'll need to think about this now. So the issue is essentially now that when we disabled just now the higher level occlusion logic for clusters that forced us to render some objects twice, we still had all of the code that rejected the individual clusters and did all of this atomic rights and stuff. All of this code was there, all of this code worked, but we were running roughly at the same speed as if we disabled everything. This suggests that the problem runs deep. This suggests that the overhead is very structural and it's going to be hard to remove it. So like, I had this other thing earmarked with using a different way to do two-pass culling, but it's now clear that it's worthless to try right now because the issue is more fundamental than this. So I was mentioning how we already measure two geometry passes separately, I think. It's just we aren't actually displaying two values in our UI, such as it is. Let's double check. Yeah. So when we call render, we already use query 0 for the first pass and query 1 for the second pass. Is 6 the query index? It's probably the query index. Let's see. Yeah. So Is there a bunch of, no, okay, cool. Let's remove this if for now. 0, 1. Our indices are very weird. So I think this is the first pass of geometry. 4, 5, 6, 7. And then 1 is the end of the frame, right? Oh, actually, hold on. No, hold on. Hold on. This is time. Hold on. So, what the heck? Wait. This code was written a long time ago, so I don't recall. It's a little weird. Let's see again. So here, when we use culling, we are writing the timestamp. Oh, right, yeah, okay. I was looking at the wrong place. This is a query, this is not, okay. Hold on. So this has write timestamp 3. This has write timestamp 7. So we do need, let's just do, okay, so let's just go wherever we have. So we are allocating 128 timestamps, so that's a lot. And then we are using 0. All right, so basically I just need to pass in the index of the timestamp here. And then I need to write a timestamp here, and then here. So then when we render, so I think we're already using 6 and 7 for the culling because this is where it's coming from. So then we're going to use 8 and 9 here, and then 10 and 11 here. So we need more here. So I said 8 and 9, so 9 minus 8, and then 11 minus 10. So I think this is what it is. This is, let's add this. All right, so this should give us slightly more details as to how much time individual stages take. We are running out of space in our debug render thingy. Yeah, so this is kind of the problem here. I think this is why things are pretty sad. This is going to be hard to, man, this is going to be, maybe our culling logic is broken in a subtle way, but if it is not, this is going to be impossible to fix. which might mean that we at least need an extra configuration boolean to like disable cluster occlusion culling globally, because, okay. So let's again disable occlusion culling. For clusters. Yeah, so here's the issue. Man, I didn't expect it to be this bad. I need to think about if this is a fundamental limitation of some sort. Okay, so we have two passes. We just weren't splitting the time that it took us to render like individual geometry passes before. We render objects that were visible last frame, and then we render objects that were not visible last frame. Okay? When we disable culling of individual clusters, it takes us like whatever it is, like 6 milliseconds, give or take, to do the first batch, and then very few time, like 0.04, almost nothing, to render the first batch. Why is that? Well, in our scene, the culling stability is basically perfect, as in whether an object was visible last frame or not is perfectly predicts whether it's going to be visible this frame or not, right? It's the same set of objects that we render, the camera is fixed, nothing is moving. It's not going to be the case in the real game, right? But, you know, it's the test that we have. When we enable occlusion culling for clusters, what do we expect on our scene? In the first pass, we render objects that were visible last frame, but not just objects, only clusters in the objects that were visible last frame, right? So it's the minimum number of clusters that we must render, in theory. And then in the second pass, we do two things. One is we render objects that were invisible last frame, but the other one is we process, not necessarily render, clusters that were not visible last frame in objects that were visible last frame. I talked about this last time. This is important, okay? You must process, you don't have to render, but you must process the clusters that were invisible last frame, because you have to confirm the fact that they are not visible. If you don't do this, there's a risk that the object was visible last frame, still is visible this frame. Some clusters were not visible last frame, but are visible now. You must render them at some point. You can't do this in the first pass, because to be able to confirm their visibility status, you must do an occlusion check. To do that, you must have a depth buffer. To do that, you have to render it from something. So you have to do this. The issue is this. The issue is that when we, so let me, what did I not? Yeah, so I have to restore this. So let's go now to the correct full occlusion pipeline. So we see that the first pass is actually reasonably fast, or it was 5 point something milliseconds, now it's 4.4. So like we are saving time, we are taking less time to render things. However, our second pass takes as much time as the first pass does. My expectation is that on a stable scene like this, the second pass should produce 0 triangles. We can confirm that, we can try to confirm that somehow. Let me think what's the best way to confirm that. We can look at the pipeline queries, which we already are computing. And we already, yeah, so we already add the pipeline results from the first and second frame. Sorry, from the first and second pass in a given frame to produce a triangle count. Let me just print, there's no space. There's no space. Let me just print these things. Yeah. So we are not rendering any triangles in the second pass. In fact, if you pipe it through more, you're going to see something interesting, and we talked about this last time, where on the first frame, the culling doesn't work. The occlusion culling doesn't work because there is no occlusion data. On the second pass, on the second frame, the occlusion culling still doesn't work because only information that we have about the prior visibility status is that the clusters, like all of the clusters, are visible. And it's only from the third frame that things start working. It's interesting that like this is sus. I would have expected this to be 0, but whatever. Let's not dwell too much on this yet. This might indicate a bug, but let's not solve this right now. So the situation that we ended up with the cluster occlusion culling is this. It does reduce occlusion culling. However, the second pass that renders the clusters and yet outputs 0 triangles is taking a lot of time. That is interesting. What I'm expecting to happen here is that we run the task shader, we do all of this culling work, and the culling work produces 0 meshlets. So what I'm expecting is that this guy is 0. Obviously, there's some overhead associated with sort of processing the clusters in this way. When I was doing this last time, I expected that this overhead would be like small enough for things to not matter as much. Like, as in, this is kind of unreasonable, right? This is almost, this is interesting. Did I do this right? I must have done this right because it's interesting that the numbers are so similar. There might be an issue. No, but we are writing. Yeah, this is curious. So the thing that's hard about this is that it's difficult for me to change this code. As I was saying, like the first 3 frames run in different states, so to speak. So it's hard for me to change this code in ways that break this fundamental structure and then test this, because things are going to be different for like wrong reasons. Okay, this is interesting. This is concerning and interesting. So the one thing I want to do is I want to add a separate boolean that I can use at runtime to toggle the cluster culling, because clearly there's like a lot of overhead and I want to be able to have this control real time. I need to think about what to do with the whole thing though. It's not easy. Yeah. Damn. So I had the idea last time, or not even last time, before I started the stream, I was like, okay, what should I do about this? So there is this false positive problem, right? You have to render objects that were visible last frame and reject their clusters essentially. What you can do is you can do this you have to render them like, because remember, so the situation we are in right now where things are exactly the same frame to frame is obviously unrealistic, right? The more realistic scenario I expect is that, for example, and we can try to do this, is that the object rotates a little bit every frame. What happens when an object rotates a little bit every frame is that some clusters become invisible and some clusters become visible. But a lot of the clusters retain their status if the object rotates slowly, right? under this, so right now our late pass takes a lot of time to produce 0 triangles. Of course, realistically, our late pass shouldn't produce 0 triangles. It should produce a small number of triangles. It's smaller than the total scene, but it's still not 0. Because of this, we are kind of running like right now, if you look at our second pass, its efficiency is catastrophically bad because we are producing 0 triangles in 4 milliseconds, right? Of course, realistically, we wouldn't be producing 0 triangles, but this does mean that it's hard to, like, there's things that I can imagine doing that make this whole problem better. For example, I can do all of this work that does culling on clusters and updates these booleans in the compute shader before we run any of this. In fact, I had, this is what I was thinking of doing, and then I had some of the ideas that would make, that would be more difficult to implement if we switch to compute shader. So I was like, well, I'll just do it in the task shader. It's not obvious. Yeah, so this is where like an actual graphics profiler, like a low-level graphics profiler, is starting to become necessary, because the question is, why is the second pass this bad, right? In the second pass, the rasterization workload should be 0. Because we shouldn't be dispatching any mesh shaders at all in the second pass after the first few frames. Because we have called all of them with like all of this bad code. But at the same time, it is hard to imagine taking this much time to do this work associated with cluster culling. Is something fundamentally bad about how we dispatch stuff? Like, so for example, one possibility is this. I don't think it would explain everything, but it would explain some things. So that's actually an interesting question. So, man, this would be brutal if this is the case. So let's do this. Hold on, let me look at the code. I wanna see. Right, so there's this DCB guy where we generate draw commands. It's in local memory. Create buffer has something where we map stuff if it's host visible. Do we use host visible buffers? Right, and then we just don't specify. Cool. So let's, I'm just sort of curious. Let's take the buffer withdraw commands. We moved it to local memory. Performance is terrible now, which is expected because this data goes. It's still not. Some performance things here, man, are just wild. What does it take 10 milliseconds to do? Does it copy the whole buffer? No. Obviously it would be slower. Oh, we have this usage bit replicated twice for some reason. Obviously it would be slower to copy this data from CPU to GPU and back, but it's a little bit worse than I would expect for the amount of data. Okay, whatever. So what I did is that I moved the buffer that has draw commands to CPU memory. why did I do that? Well, after the frame is done rendering, and we wait for the GPU to finish whatever it was doing, which we already do here, we have an opportunity to compute some stats. Specifically, if you look at the draw commands, this is the guy. There's this inefficiency, which we have never fixed, but anyway. So if we look at this command, we can look at a few things. One big thing that we should care about is what is the configuration that the how many task shader invocations do we have? And there is this thing called Boolean valid here. Why does it matter? So let's say you have three meshlets that you want to render from a draw call, only 3. Well, the issue is you have to dispatch the culling shader, or the task shader, sorry, in work groups or in thread groups. And as I was saying, so like this thread group right now is 64 threads. This means that when you dispatch the task shader, you can only dispatch 64 threads minimum in our configuration of work. But you only have 3 meshlets to render, so what do you do? Well, so what we do is we take the number of meshlets that we want to render, we round it up to 64, we dispatch the number of work groups that are needed to process this much, and then the last work group in the set is doing only a little bit of work. For example, if you only have 3 meshlets to render, then you dispatch 1 work group, and then 3 threads out of 64 in that work group are doing work, and then the other threads are doing nothing. If you have a lot of meshlets to render, like 10,000, then it doesn't matter as much. You lose a little bit of time in this last work group. But if you have 3, then it's pretty bad, right? So the efficiency of our current pipeline from this perspective, not from the perspective of the number of triangles that we've talked about a lot before, but from the perspective of the number of meshlets, is critically dependent on this amount of sort of waste that we generate when rendering things. So I kind of want to compute how many meshlets do we process total in a frame in the second pass, which is important. Is it important? It's going to be roughly the same. It doesn't matter if it's the second pass or not. But how many meshlets do we process versus how many how much work, sort of how many work groups do we actually dispatch? Because if these numbers are really off, like if we have an average of 3 meshlets per draw call that we produce, then our culling, then in the second phase, the efficiency is going to be terrible. Maybe when you render triangles, some of these problems are masked by the fact that you're rendering triangles. So you're occupying other units on the GPU with like useful work, but it might be bad. On the other hand, if it's a lot of meshlets, then it's not going to be a problem. So I think this might be an issue that we're running into. Let me try to confirm this. The other thing I need is the counter command buffer. Oh, I should have checked in. I should have checked in the timing code. I will roll this thing back later, so it's fine for now. Okay, so now that these buffers are host accessible, what we can do is we can say DCCB data, and then you have to cast it to period. The stream is not going in the direction that I thought it would go, but hey, that makes it more fun, I guess. All right. So let's read just this guy to see that the whole setup works at all. Oh, sorry, I have to remove more. Okay, so we're rendering around 20,000 commands in the second pass and probably in the first pass as well. When we disable occlusion culling, we render 0, so that checks out because this is just data from the second pass. 20,000 is probably right. Who knows? we are definitely in danger zone. So we have 9 million triangles before occlusion culling, I think. And 3 million, oh, but this is with, no, it's hard to know. Let's just compute the number. So we'll have two things. We'll have draw meshlet count, and we have draw meshlet invocations or something like this. The reason why we can just write this code here is that because we are not, normally you would, normally the GPU would be processing one frame, and then the CPU would be preparing the next frame for rendering. We aren't doing this for simplicity of synchronization and stuff like this, which you will never do in a production application, but it's fine for us for now. But this is why at the end of the frame we can just say, oh hey, let's just read some data from some buffers and then compute some numbers on them. So and then I want, do we even have, is this the struct? Yeah, I think this is the struct. I guess I can just do mesh drop. Hello, my keyboard is not cooperating with me. So DCB data is the thing we care about. Oops. And then task count, and then task x times 64. So if you look at the shader, then the way we dispatch this is this. So this data is the data that is actually used for by the GPU to figure out how much work to dispatch. And we dispatch these groups that have the dimensions of all groups are 3-dimensional, but this is just a weird artifact of however the API was designed many years ago. Realistically, you just set the last 2 to 1 in our case. So we take the number of meshlets, we round it up to the workgroup size, which is 64, and then you divide by 64 to get the number of workgroups, and each one has 64 items to process. And then we also save this guy, which is the real number of meshlets that we really need to draw, or to process, I should say. And that is what is going to be used in the shader to figure out, oh, do we actually do work on this or do we skip it? So if we add up both of these, then we can say what's our sort of efficiency, right? So meshlet count, meshlet invocations, ratio, let's do this. It's going to be count. Called something else on the CPU. Indirect MS group count X. So this is not too bad. This is not too bad. I was worried that we are losing a lot of efficiency on what is essentially small draw calls. But it looks like it's okay-ish. As in we are processing, like the ratio is 88. By the way, if you disable level of detail, this should be better, right? 88.5. That is weird. What? Interesting. Maybe our last, so it could be that our level of detail curve is kind of conservative. Oh, and we have this far plane that is artificially reasonably close by. Yeah, okay, so this probably checks out. Okay, this can be a problem. If this number was like 10% of whatever, I would be like, whoa, we need to rethink how we do culling and whatnot. There is like, there is a way there is not, how do I put this? Like, in theory, so right now we are in a situation where the task shader only ever processes a number of meshlets from the same mesh. Technically, this doesn't have to be the case, I suppose. You can group things. It's hard, it's painful to do that though. Like, there's things that get more difficult once you do so. But it doesn't look like that's a problem. So then it's really suspicious because we are taking, we can do some numbers on this. So the average, it's interesting, the average is 66 meshlets per draw call. How is the ratio so good if it's 66? Because it's right above the border, the cutoff. Oh, I guess it's, I guess it makes sense. All right, so then for every draw call, we dispatch like a couple of waves of task shader work. It feels likely that for many of them we dispatch just one. We can compute this number directly. Single group. Yeah, so out of 19 or almost 20,000 draw commands, almost 17,000 draw commands only dispatch a single work group. Yeah, it is possible that this kind of dispatch is just super inefficient on AMD hardware. So when I think I have deja vu, like years ago when we started the series, I think we might have looked at the inefficiency concerns on NVIDIA hardware, but this was a while back. This was a different vendor, but there is this question, right? So you have the task shader, and then the task shader dispatches mesh shaders, mesh shader invocations. How efficient is this dispatch? If I have a lot of small task shader work groups, is it bad? Is it good? Who knows? Yeah. So it is possible that on AMD it is inefficient to do some of this stuff in this way. But it's hard to pin the inefficiency down in the sense that this does need a low-level GPU profiler that actually has support for mesh shaders. I'm not even, so I don't know if RGP even supports it. Let's look into this. Radeon GPU profiler. So the first question is, does it work with RADV at all? So there was some support for it. So it's hard to know. It might work. Even ray tracing works. Okay, so this might work. My second question is, does RGP support mesh shaders at all? Is there a full release? So this is just for this one, a version history. I mean, my best guess is the answer is no, right? Mesh shaders and Vulkan exist as of mid-21. It would be strange to see support for this added before. It doesn't even mention DX12 mesh shaders. Yeah. We kind of may be out of luck with RGP. Right? Without that support, it's going to be impossible for us to diagnose the specific problem that we seem to be running into, which is that whatever is happening under the hood for the actual mesh task dispatch, in our specific configuration, which says here's a bunch of draw calls, for every draw call that's dispatched mostly what looks like one invocation, one thread group with task shader work. There we are going to do parallel processing of the individual meshlets, because we do have, it looks like I don't know, 50 or so per draw call. Call them. All of the calling results say dispatch no mesh shaders, and that's it. So we don't even run mesh shading, mesh shaders at all in the second pass, but this whole pipeline takes like a lot of time. There is a way to accelerate this probably. It's just, oh, I'm wondering one thing. It's a stupid thing, but I'm just wondering one thing. The thing I'm wondering is, like, can you just like skip? If a work group has 0, I'm not brave enough to test this, because if this can't work, then the GPU will crash. But I'm just wondering if you just never call this guy. Is the fact that we are calling it with 0 a problem? Yeah. I don't know how to investigate this further. I don't know how to investigate this further. Like, I need to think about how to investigate this further. There's maybe some amount of like thinking about this and reading the driver source and stuff like this that could help. Here's the crux, I guess, of the problem. Imagine this was running in a compute shader that did like the same work. The nice thing about that is that we it's hard to do this. Like, it's possible to fix hypothetically. Like, so here's the interesting thing. On AMD, there is no task shaders. Task shaders are just compute shaders. So what the driver does is it compiles a compute shader for this. Then out of this task shader. And then this compute shader writes, whenever you say, oh, I want to like emit mesh shader workload, I think it's filling commands. I don't know how exactly this works. I haven't read the driver source, but sort of on a conceptual level, it's emitting commands for the GPU to actually dispatch the mesh shading workload. Oh yeah, I think actually, sorry. I think the way this works, I sort of remember. I think the way this works is that there is a, because they use gang submit. So I suspect what might happen, I need to go back and read this. I wasn't really focused on this part, but I suspect what happens is there's a mesh shader like running that is waiting for work, and it's trying to read this work from a ring buffer, and then this ring buffer is being written to by the compute shader stage. And then this compute shader stage, in this case, produces no work. But right, so like it's not clear. Should you just skip the entire call if there's nothing to do? Is that like a problem? Or one possible source of this whole issue is that we are running in this interesting configuration where there's a single. We can do some numbers with LOD disabled. Maybe that'll tell us something useful. But right now we are running this configuration. We're running this whole thing in a configuration where we are dispatching a lot of small work groups, independent work groups of task shaders. If that is slow at all, for some reason, maybe we are being bound by, like, I don't know, the processor of draw calls, because we are trying to render 20,000 draw calls. Like, it's not a small number. And because we have to do them in the second pass, this reduces efficiency in some sort. So let's say we don't do that. Let's say we do a compute shader that somehow in one invocation fills all of these booleans with data. Well, we still have to do a pass where we still render objects or clusters of objects that we thought were invisible but are actually visible. It's possible to do all of this at peak efficiency, meaning you can run a compute shader, a single dispatch of a compute shader that computes all of these bits, because you have to do this work anyway. And then you can say, well, now for every cluster, let's do culling again, sort of, where we read all of the bits corresponding to a draw call, and if only some of them are set, then we will dispatch some work for the task shader and otherwise not do that, which essentially here might solve this problem, because it will turn the situation from, oh, we have a lot of small task shader invocations, to we have done some work to make sure that there's nothing to do, and then dispatch no task shader invocations. But this is a lot of work. This is like a lot of writing code. I don't want to do that. And I don't know if it would help, because I don't know if this is where the problem is. And again, right, so the lack of the profiler that will actually tell us detailed information about what happens specifically around task shading and mesh shading and whatever. Like, it's not enough to just have a GPU profile. We have to understand why the problem is there. And it sounds like RGB doesn't support this stuff yet. Okay. Yeah. I don't know what to do about this. The good news is that the operation, the good news is that it's easy to add a switch that just disables occlusion culling for clusters. This problem might not be a problem on other GPUs. For example, as I mentioned, I will have an ARC GPU at some point soon, hopefully in a week. And then if on ARC, in general, things work in this space, then maybe we will not have this problem there. Who knows? It's like an exciting field of uncertainty. But maybe Intel will have problems in this area or in some different areas. It's hard to know. But yeah, I don't know what to do about this right now. There's things I could imagine trying that take a lot of code. There is nothing that I can imagine trying that doesn't take a lot of code. Yeah. There is nothing I can imagine trying that doesn't take a lot of code. Even splitting this, so if splitting, the only thing that is simple-ish to do, is this. Right now, this shader, this might be fruitful, who knows. Right now, this task shader is doing like everything, as in it's doing culling, updating booleans, and then dispatching work for the mesh shader. You can take the actual compute part of this, separate this in the compute shader, write the booleans, and then the real task shader is just going to read the booleans that were computed in this buffer, and then based on whether they are set or not, decide whether we need to render or not. The problem is that we might still have the issue, because who knows, maybe the fact that the task shader is running at all is like a problem, and then it doesn't matter how much work you do there. It's hard to know. The second issue though is that to do this, we have to run the compute shaders. And we use indirect dispatch. So this is getting into indirect compute dispatch territory where we have to change the calling. Like, it's a lot of work. Like, we can do this, but it's a lot of work, because we have to kind of change the whole structure of what we are doing to incorporate this extra separation, which is bad. Okay. So I don't like any of these options. The only option that I do like is to add a way to control the occlusion culling of clusters from the CPU, so that we have a way to toggle it, and like, so that we don't have to change the code all the time to figure out what the efficiency loss is, and park this problem. Like, there's not a clear way to resolve this. I don't see one. Yeah, I'm using 6700 XT right now. It's an AMD RDNA 2 GPU. Man, I was counting on the memory traffic around this horrible buffer being the problem, and then I had ideas around this. But if the problem is more fundamental, yeah, it changes a lot of the fundamental assumptions. Okay, sure. Okay, so the upshot is then, so we are not gonna even try this. We're not even gonna try this because that's clearly worthless now. We still can, so this, there is a giant question mark here, because I was hoping to refactor some code around this two-phase dispatch, but I wasn't planning on rewriting it completely. And now, depending on where the problem is happening, like why it's there, we may or may not need to do this. It's hard to know. There's still some tactical refactor that we can do, but it's hard to know. We are like 2 hours in. I don't want to do this one either, because I actually tried this off stream and it wasn't super. I was thinking that I would talk about this a little bit, but it hasn't helped, I think, at all, because of like reasons. I actually don't know why it didn't help. So maybe I should still try this. How do I undo this? Okay, let's do this. Let's set a boolean quickly so that we can disable the stuff. Let's commit some code that we can commit, and let's talk a little bit about some mesh shader stuff that's going to be more tactical. And then we'll see. Okay, so I need to undo some things. So I need to make these guys device local. All right, so we are back to like 9-ish milliseconds. So this was redundant here, so that's fine. So we added timing, which is always good. Adding per stage timing allowed us to very precisely diagnose the problem, which is nice. If we had it earlier, things would be a little bit easier, but the crux of the problem hasn't changed. The crux is, wow, this is going to be difficult to resolve. Okay. Now, because of this, I want a way to completely disable. There's a way we have a boolean to disable occlusion culling. However, the occlusion culling on the draw hole level is actually super good. It costs very little, and it saves us time. The cluster of occlusion culling is more complicated, turns out. Wait, so let's add a separate boolean. We are going to have to add this to something. This is going to be so we're going to rename this guy because I'm going to rename this guy. I'm going to add this guy here. I should have committed, sorry, hold on, go back. I should have committed the code in the working state. Add early, late separation for render time stamps. This allows us to more precisely diagnose issues, performance issues with occlusion. Okay, so cluster occlusion, and then we have to invent a key that we are not using yet. C is taken and O is taken, and L is taken, and M is taken. I'm out of ideas. Let's use K because cluster. Okay, so then where else do we use this guy? Now, cluster occlusion culling will only work if occlusion culling is enabled. So whenever we use this guy, we are going to check both. Oops. Okay. I don't think we need, right, so then we need to print the status even though it's going to be impossible to see because yeah. Okay, so then we made some changes that we have to replicate here. So we've added cluster occlusion here, and we need to rename this guy, but this could happen later. Okay, so now we have to fix shaders because they reference this guy. All right, there's a little bit of a wasted work. We can check this boolean here. This visibility status is basically all operations around this guy. We only need them if cluster occlusion culling is enabled. But it's probably fine to occasionally do them even if it's disabled. Like we are skipping the occlusion check, and the most important thing, as we realized, is that we skip it here. Oh, sorry, cluster occlusion. Okay, so I think this is correct. This is not correct. Oh, it's it wants something. Didn't I add %s? Late. What? This is I've never seen this warning before. This is a first. I see. No, there's 256 bytes. What? I mean, okay. Sure. Should use the send printf. Okay. Interesting. Is that what it's doing? So it statically analyzed my format string and decided that it doesn't fit into 256. Oh yeah, it's actually right. Oof, it doesn't fit. Okay, all right. So now if I press K, yay! So if I press K, the GPU time goes down to 7 milliseconds ish, and if I press it again, it goes up to 9. And then the number of triangles is correctly adjusted. Okay, so we can now, I can disable occlusion culling entirely, but that is not beneficial because it takes 10 milliseconds to render the scene. I can enable it on the cluster level and draw call level, but on AMD hardware right now in our implementation, it's actually best to disable cluster occlusion culling, but enable draw call occlusion culling. Okay. And then let's kill the sprint. This guy, we don't really need it. Okay. Allow individually disabling cluster occlusion culling, press K. This helps us on AMD hardware where our current implementation is very suboptimal in the late past for a reason yet unknown. Okay. So this this whole thing was demoralizing, if I'm being very honest, because we essentially spent a bunch of time to reduce the memory impact, which was good, but then kind of failed to actually fix the performance issues, which requires more investigation. So that sucks. There is one thing that somebody suggested to me on Mastodon that I thought we can try, which was this. So, sorry, one thing I want to try quickly. CS-Wave32 or something. Don't know if that actually worked. Okay, never mind. Just pretend that I did nothing. Okay, so there's one thing I want to try. Oh, let's actually go one step further and let's disable cluster occlusion culling by default, because all of the previous optimizations that we've added, they were positive sum in a sense. I was talking again. I keep repeating myself, but the work required to do a certain level of culling has been smaller than the savings that we get in future stages. For occlusion culling right now, this is not the case on AMD hardware. So conservatively, let's disable it by default. You can still enable it and then disable it at runtime now. But by default, we'll keep this off for now. Again, I'm hoping there's probably a way to not have to do this, but I don't want to do this right now. Like it's more difficult than we have time for right now. Okay, so somebody on Mastodon suggested an interesting idea that I thought I would try, which is this. The way we have implemented culling is by using this part of the extension, which is glcall primitive ext, which allows us for every triangle that we output. Sorry, this is like a reset. Forget cluster culling for now. Occlusion culling is weird. We'll come back to this hopefully at some point if I figure out what the problem is or whatever. But on the string before that, so the one before the previous one, we've implemented triangle culling in the mesh shader, and that worked well. And the way that works is that for every primitive we are setting a boolean that says whether the thing is visible or not. Somebody suggested a possible alternative where instead of using this built-in boolean and setting it for every triangle that we output, we instead do the culling work, and then instead of saying triangle number 0 goes into Meshlet output number 0, triangle number 1 goes into Meshlet output number 1, but by the way, triangle number 1 is invisible. Triangle number 2 goes into Meshlet output number 2. Instead of doing that, we can only output the visible triangles. Okay? Oh boy. This has to be called before, right? Because it like allocates. Yes, so this requires us to do this culling work before we establish the output number of triangles. So it requires like reshuffling the mesh shaders and stuff. I am hoping it doesn't actually end up being beneficial, but you never know, so I kind of want to try this. Because of the change that we've just made to the configuration of the mesh shader, things are simple. We have a single thread group that has 64 threads that process 64 vertices and 64 triangles, which means that we have an excuse to use Ballot again, and you know, I guess that is good. We aren't using Ballot now, by the way, but we are using. Oh no, sorry, this is different. This is for the okay. So. Okay, so the downside is this. I think you must call, like, there is no separate value, right? I think this is just, let me read the spec again. This is the wrong. Yeah, there must not be any control flow path to an output, right, that is not preceded by this instruction. So I think this is different between the NVIDIA extension for mesh shaders and the Kronos extension for mesh shaders. But in the Kronos extension for mesh shaders, you have to call this guy, and only after this you get to write to any outputs. And you can only write up to this number, right? But we have this interesting case now where the total primitive count is different from the max primitive count. But to compute the total primitive count, we have to transform the vertices to clip space. So this is fine. Essentially what this means is this. We have to change how we do things a little bit. What is this? Why is this here? So let's move this guy here. And then we first go through all vertices, we take the index of the vertex, we fetch the position, and then we transform this position to clip space, and then we only need to do all of this when culling is enabled, and then we write this to our shared array of coordinates that we have for every vertex of the meshlet. Okay, now that we have done this, we can run this code and determine the output number, the total number of triangles that we output, because we can run all of the calling logic, and then we can use various Ballot instructions to figure out how many triangles that results in, and then we can probably use the Ballot thing to somehow, for every thread we have to, oh boy, the problem is, oh no, actually this is fine. Yeah, okay, this is fine. Okay, let's try this. So, first, let's just change the shader to do the same thing that it was doing before, but sort of in different order. Yeah. So now the flow is we transform the vertices, then we set the number of outputs, then we write the attributes, and then we write the indices with culling. We're going to reverse this in a moment. This should still work. And it's slower, which is interesting. Is this because we are doing redundant transformations? Man, this whole thing is fiddly. Okay, so let's say, oh, but then we pre-divide here. Ah, this is terrible. Okay. All right, this was fun. So this is now slower. We used to run it around 7, and now we run it around 8 milliseconds per frame. The obvious reason for why this might be slower. Oh, we don't need this extra beta. I don't know what this is doing here now. The obvious reason for why is that we are now doing the vertex, the position transformation twice, and we're also reading the vertex data redundantly. Yeah, so we can fix this. Oh, I'm technically doing a somewhat redundant thing, but I don't wanna mess up the code too much. I think we're gonna probably revert this whole thing, but okay. So let's see. Let's fix the redundancy of the transformation. Right. Okay. Still a little slower. It's faster than doing it twice, but it's like 7.5, 7.4, 7.6. Okay, that's fine. Let's keep it this way for now. I'm just curious if this, like, if now changing the calling to compact stuff does anything. Because if it does do something, then maybe there's a better way to organize all of this to do zero redundant work. But for now, I don't care as much. So let's take a note here. So this is 7.40 something, 7.42 is around the stable point. We really should change the timing code to like display a single stable number, because it's difficult to make on the spot decisions like this with the number fluctuating. But so now our goal is this. Now our goal is that we are gonna write, we are gonna run the calling logic after we have computed the projected coordinates of the vertices. But instead of writing anything anywhere, we're just gonna compute the mask. And so this thing bothers me. Okay, I don't know. All right, I don't know. I'll think about this one once I write the code. So when culling is enabled, instead of working with this built-in like Boolean thing, we're going to compute the culling, and then we're going to use this magical Ballot instruction. I don't know what happens for inactive. Oh, right. Right. The way we solve this without thinking about this a whole lot is this. Okay, so now, oh my god. All right, so now we have the Boolean that we have computed for every triangle. And then we are gonna compute the Ballot of the Boolean, which is just gonna take, as we were saying, this Boolean in every thread. There's 64 threads, and it's gonna create a 64-bit mask. This guy has 128 bits worth of storage because it's 4 32-bit integers. So .x and .y are the things that the Ballot has computed. Now, why do we even need the Ballot? We don't need the Ballot. There must be. This is the thing that we act. Oh, I see. We do need the Ballot. And then we have to use this. Okay, cool. We are doing everything correctly. Okay, so now we need to compute the total number of triangles that are present in the meshlet. Well, is it safe to like overwrite this guy? Sort of safe. Okay, so to do that, there is this function that is going to count the bits set in this value that Ballot returned. So essentially what we've just done is we've said, well, in every thread we have computed this Boolean. Oh, sorry, we need to invert this. Hold on. Oh. Okay, we need to invert this. We need like visible Ballot. So we need to have one for every visible triangle in this mask. Now we are saying for every one, treat every one in this mask as a bit, and then count the total number of bits, and this gives us the triangle count, which is the number of visible triangles here. Okay. Now that we have the number of visible triangles, instead of outputting them, now we don't need to run the culling again. But what's worse or better, or like there's one other thing we have to do, which is this. So imagine that we have these threads that are 0 to 63, right? Imagine that thread 0 said visible is true, thread 1 said visible is false, thread 2 said visible is true. What previously happened is that every thread just wrote the primitive into the output that it wanted to write to, and then it and then it set the culled Boolean to like 0 or 1. Now what has to happen is a little different. Now threads that have computed the triangle as invisible shouldn't do anything at all. So let's just change this to not culled. So if we haven't culled away the triangle, which means the triangle is visible, I'm playing fast and loose with this cull define, like this is an irreversible shader modification that I hope is not faster, and so I hope we don't have to clean it up and commit it. But so if the triangle was not culled, what we're going to do then is we're going to load the triangle as usual, but instead of writing this to the location that is denoted by the thread index, we have to instead write it to the index of the we are compacting the triangles, right? So like in this 3-thread configuration, what we have to do is we have to write 2 triangles to the output, one corresponds to the thread 0, one corresponds to the thread 2. So in the thread 2 here, we have to compute the right location, which is 1, not 2, because it is however many threads have written stuff to the output before. So, which means that when we are writing this primitive, instead of writing to the index I, we have to write to the index right. And right has to, there is a Ballot thing for that, which is this guy. So what this does is this. It counts all bits set before the thread that is calling this intrinsic, and then adds them all up. And so here in the thread 0, it's going to return 0. In the thread 1, it would return 1, but we aren't even asking in the thread 1, it doesn't matter. In the thread 2, it's saying, this is what the exclusive stands for, it's saying add all of the bits before this bit, not including this bit. Anyway, which is exactly what we need. So I think this is probably correct. If the stream, what is screen? If the stream crashes right now, what this would have meant is that we got this shader incorrect and something went horribly wrong on the GPU and we couldn't recover from it. Right. We need to request it. I think we probably are requesting this. Yeah, at some point Ballot used to be used in the task shader. The thing that's hard about all of the subgroup stuff is that it's not portable across different subgroup sizes. So right now we are taking advantage of the fact that we know that on AMD hardware on our driver, subgroup size is 64. And our thread group size, like everything is 64. Any number that you can think of is 64 right now. And this makes things way easier because it makes things very predictable as to how things behave. This is not true in general. This code will not work on like Intel or NVIDIA hardware. So, and this is why it's hard to commit it. But let's first see if it even works. This B. Hey, it worked. I was saying 7.4 milliseconds, right? I mean, it might be a little bit faster. It might be 7 point. It's fluctuating like crazy. It might be 7.3 or something like this. Nah, not really. Yeah. So there's not like an obvious. The correct thing. Oh, is it a triangle count correct? By the way, yeah, 6.66. The correct thing to do here would be to do a precise. If we used RGB, but there's problems with mesh address, as I was saying, but even if we didn't use RGB, there's ways to answer the question, did we make things faster in a more precise manner? You can look at the histogram of times, you can compute properties of this, like there's a way to answer this question. However, for us, we don't really have to do this because the thing is not like obviously faster than the version of the shader that had this double computation of positions. But if we actually revert to the thing we used to do, which is just stashing this thing and then running it again, then we ran at under 7, slightly under 7 milliseconds. So this actually makes the code slower. It's not because we are compacting the output. Compacting the output by itself didn't seem to do much to the performance. It's because in order to compact the output, we had to restructure the shader computational flow, and doing that made the shader slower. And it's sort of possible to recover from this, but not very, like, there's stuff that the shader had to do twice now. For example, it had to read the index data twice. You can fix this by storing it into local storage, but like it's all a lot of work, and it looks like this work doesn't actually produce a meaningful speed up or any speed up at all. Okay, so the theme of today's stream is we do stuff, it works, it does nothing useful, but I actually expected this for triangle compaction. I'm just sort of happy to be proven. I didn't expect it to matter a whole lot, so I'm glad that it doesn't. There's actually, by the way, I think there is a boolean in the mesh shader extension somewhere that I don't know how to find it now. There is a boolean somewhere that says prefer compact something something. Let's actually see. Yeah. So the way the Kronos extension was written is that it has a bunch of tweakables. It has a bunch of booleans and a bunch of numbers that it exposes from the driver. And these are purely informational, but they are designed to tell you information about the efficiency characteristics of the hardware that may differ between different GPUs. For example, it has this thing called prefer local location, vertex, and primitive output, which we haven't talked about. We will have to talk about this at some point in the future stream, because this was related to me adjusting the numbers that I adjusted at the very beginning of the stream. But it also has these two booleans that says prefer compact, vertex, and primitive output, which is interesting because it says should they be compacted after custom culling in the mesh shader for best performance. Otherwise, the use of call primitive ext may be better. This thing is exactly what we've just done. We used to use call primitive ext, and instead we said, well, you know what? Instead of that, let's only write the visible triangles to the mesh shader output. And to do that, we had to restructure stuff. So there is an interesting question, which is what is this value on our driver? Because it didn't help, right? And in fact, it hurt, but again, it hurt because of other reasons. So I don't know if Vulkan Info supports. Perfect, it does. Aha! Our driver tells us that this was a bad idea to begin with. Our driver tells us do not compact primitive output. Which is great because it's correct advice in this case. We tried doing this, it made things a little worse, meaning we shouldn't do this. There are drivers that can, like this driver says false, there's probably drivers that say true, right? So it's an interesting question as to whether you still want to do this on other GPUs. But for us, we don't want to do this. This thing, interestingly, says prefers compact vertex output true. This stuff is hard. Oh, I just had an interesting idea. We are gonna try something. I had an idea. We are gonna try something. No, but this can't possibly make sense, right? It's not a great idea. Well, it'll tell us useful information, so maybe we should try this. It's non-trivial to try, sort of. It's possible to try. Maybe we will not try this. The stream is getting long, so I had an idea. Maybe it's a good idea. Maybe it's a bad idea. It's not a good idea in the sense that it won't make things better. It could tell us some more information about the previous issue that we were investigating. But anyway, sorry. So what I was gonna say is This driver tells us that when we do custom culling, we should try to compact output vertices for best performance. What this means is that the thing we just did with triangles that didn't help, you can try to do a similar thing with vertices, where instead of saying I have 64 vertices to output and then only using like 40 of them, you could try to say I only need 40 and then reorder things correctly. This is a little annoyingly difficult, because we don't call vertices, we call triangles, right? And it is likely that the meshlets that we output don't use some of the vertices that we output. But to actually be able to discover this, we have to take the results of this culling, which are per triangle, and then ask a different question. The question is any triangle that is visible using a vertex number x? It is possible to answer this question. It is a little frustrating to answer this question, because you have to aggregate, like it's not, I mean, we can use subgroup ORs or something, like it's definitely doable. Maybe the driver even does this when we aren't using mesh shading pipeline. You can use atomics, there is a subgroup OR. So you can do, oh, this is inclusive OR. This is not what I want. I want like a flat OR. This subgroup stuff goes deep. Is there no way to OR stuff across? I mean, I guess I can do bit count. The stuff I can, okay. I don't wanna, oh yeah, there we go, subgroup OR. Yeah, this is what I was looking for. So yeah, so you can absolutely compute this. It's a little annoying that the numbers are 32-bit, and you kind of want to use 64-bit math to be able to do these operations. There's probably some way to use Ballot as well. So there's like ways to do this. I don't wanna, it's been 2 hours, 40 minutes. I don't wanna do this right now. But like in theory, you can try to compact vertex data. It's just really awkward. Like I don't like doing that. And the other thing, I didn't find this in the spec when I was looking. I can try to do this again, but here's the other question. So let's say you, there's 2 things you can do. Let's say you are never using vertex number 5. There's 2 things you can do. One is you can not output it at all, meaning you can not run this code. The other thing you can do is you can not output it at all and do the compaction that we were just doing for primitives. The first one is much easier to do than not much maybe, but the first one is easier to do than the last one because it's less work. Like you just need to figure out if you need to run this code. However, it might be the case that it's not defined. Like if you said that you're gonna output 5 vertices, you might have to output 5 vertices. I don't know that. And I didn't find this like off the top of my head in the, it should probably be in the SpirV extension actually, not the, stuff is all impossible to search. Yeah, I don't see here. So this is not the spec. Technically, this is like a high-level description of the extension, I believe. Somewhere else, I guess maybe in the main Vulkan spec. There should be. Alright, whatever. I don't want to go find it. Essentially, the question is it undefined behavior to just have vertices that you're not referencing with triangle indices, but that are in the array or not? If it is, then it's a problem. If it's not, then maybe we can do a weaker version of compaction. But does it save us time? Probably not. So anyway, alright. I am getting tired. So if we look at the, so we didn't do, so I don't want to do this because it's just not going to be useful. We did add a boolean to disable occlusion culling, which is cool. To disable cluster occlusion culling. I don't think in a given state there's a whole lot to refactor though, because so this thing is correct. In fact, we could skip mesh shading enabled check if we can now do this on the CPU, because we can set this guy only if mesh shading is like actually enabled. Let's do that. Cluster occlusion enabled, mesh shading supported, mesh shading enabled. Oh, this means we don't need this guy, I think. So that's cool. Okay, so yeah, I think that's cool. That's true. Oh, where is this guy? Okay, cool. So that is good. That is a slight simplification. Okay. Okay. So, but this logic has to happen here. Then in the task shader, we do this check. And then there is some code in the task shader that's positively weird, like this stuff. But I talked about this last time. We sort of need it, kind of. There's maybe a way to formulate this, but like in the late pass, we have to skip the clusters that we have already processed in the early pass. There's no option of not doing this. So this is not negotiable. Like, you have to do this. You have to do this check, because if you don't do this check, then if the object wasn't visible last frame, the visibility bit from last frame is going to be bogus. So you can't really use that. So you have to have this code as is, pretty much. There's not like a good alternative. You have to do this. The heck is this for? If you're in the early pass, we mark things as invisible if they were not visible last frame. Right. Again, there's no option of not, like, you have to do this. Because that is the check that we use to figure, yeah, like we have to. Okay, so I don't even think this to do option is relevant. Like, this has to happen here. We can add a comment saying, let's add comments. So in early pass, we have to only render clusters that were visible last frame. We can render more, but then we are like very inefficient, to build a reasonable depth pyramid out of visible triangles. Also in late pass, we have to process objects visible last frame again after rendering them in early pass. In early pass per above test, we render visible clusters. We render previously visible clusters. In late pass, we must invert the above test essentially to not render previously visible clusters of previously invisible objects because they were rendered in early pass. So this is not optional. Like, the logic is convoluted, but it's what it has to be. There's not an option of changing that, unless we split this whole thing into a separate pass. But then there's going to be convoluted logic in a separate pass, which is not a clear win. So the one thing I should note is that we don't need to do this stuff if occlusion culling is disabled. Neither this check, which we are checking here, nor this check. I don't know if it is correct to do this here. I would feel better if we skipped all of this stuff. So only if global's cluster occlusion culling enabled is 1, do we need to fetch this and then do this, and then do this. So this is kind of what it is. It has to be this way. Then we can reorder this, I guess. I guess we can also add this check. I don't know if we are making things better or worse right now. We should check perf. But now, if cluster occlusion culling is disabled, we are not going to do any work. We are going to dynamically skip. Let me rephrase. We are going to dynamically skip any work that is relevant to the cluster culling, unless we have to. We can explore building a specialization of this, but you know, things sort of work. This is what it was, yeah. I think. Okay. So that's kind of that. So the other thing we can do is we can stop using this thing and so at the minimum, let's rename this to just late, I guess. Late pass. Okay. Okay, so this is some minimum refactoring. It's kind of like we have to keep this logic in its current state, more or less. There's not like a good option of not doing that. So let's do that. We kind of have to preserve existing logic more or less as is, but this adds some comments and renames some variables. And then one final thing that we can try to do, which is it worth it? Is it not worth it? I don't know, probably not. But we had this whole thing around using specialization constants, and there was a bug in AMD drivers on Windows at some point around this. I confirmed that this bug existed as far as mid last year. Since then, this bug did not exist on the Linux drivers that I'm using. It never existed, as far as I can tell, on Linux drivers that I'm using, rather. But also, I tried to confirm it on AMD's Linux drivers, AMD VLK, and it also didn't happen. It's possible that AMD has fixed it. It's also possible that it still happens on Windows drivers. The thing, though, is like, you know, if it still happens on Windows drivers, we can put the workaround back in, I guess. But what we can do is, instead of using, so right now we're using this runtime check in Task Shader to remove work that has to do with cluster occlusion culling. Most of this work is also gated on this. Most of the work only has to happen in the late pass. Only in the early pass, the only thing that has to happen is we read the visibility bit and we hide the cluster if the visibility bit tells us that it should be hidden. But then in the late pass, we do a bunch of other stuff, including like sampling depth and doing atomics and whatever. Now, we now have dynamic checks around all of this that disable this if cluster occlusion culling is disabled. However, we might as well use the static checks, as in we can use a specialization constant and then compile the shader twice with it false or true, and then maybe some things will be a little faster. To get that to work, this would mean that we don't need all of these booleans, which is nice, and the C++ code may become a little simpler. Does it make a difference performance-wise? Probably not, but it feels a little bit better to not have this redundancy, I guess. So let's try to do this and then see what happens. So essentially, for this to work, we need two pipelines. Mesh pipeline and mesh late pipeline. And we have this, essentially we added support for specialization constants a while back. So we're just gonna activate it for the mesh shading pipeline that we use. And then whenever we use mesh pipeline, which is in one place, we have to use, is there a late boolean? There's a late boolean. All right, so this is swapping basically some runtime checks inside shaders with compile time checks that may or may not make things better. Things still work. Yeah, it looks like about the same level of performance, which I expected. The reason why it feels nicer to do this is that it's hard to know. So like for a lot of changes that we make that are performance sensitive, there's a question, do they help performance or not? Unfortunately, the only way to answer this question is to test on a GPU. But the question is on which GPU. Because it could be that in some cases, the fact that we have additional atomic writes, even if they are behind like a runtime check, maybe that's a problem because maybe that restricts scheduling of some shader in some way, or maybe it doesn't. I don't recall why we added the specialization constant to the culling shader to begin with. But for some reason we did this there, and so it feels like we should either use the same. It feels like we should use the same technique basically in the mesh shader and in the task shader and in the culling compute shader. It's just, should it be specialization constant or should it be a runtime check? Who knows? It's hard to check. It's hard to know. For now. Yeah, that is something we'll still have to do. For now, this seems reasonable. I'm making this a separate submit so that if we discover that this was a bad idea, we can just revert this commit and that's it. Place late. And it was always meant to be a specialization constant. It's just we had to swap it out for AMD drivers on Windows to work and never bothered switching it back again, so. This doesn't seem to appreciably change performance, but you never know. The reason why, so in task shaders, the performance is more important now than in this culling shader. It runs way more often, etc. So there might be small effects on things like, so you have a runtime check, and you may think, oh, you're setting the boolean to false. There is no overhead anymore. Well, the GPU has to do the check at runtime. But the more important problem is, for example, you have to compile the code that would have executed if the boolean was true in the same shader, and that may increase the register consumption of the shader, which may reduce the efficiency with which the shader runs on hardware. So, like, this is why it feels like we should be careful about what we do in the task shader more so than we are about the compute shader. That said, none of this actually seems to be helping performance in our case, so maybe none of this is actually important. Anyway. All right, so I think that's kind of it. Let's just claim the biggest reason why I did this is that so we can claim that we have heroically refactored the two-phase culling. Why am I? Well, right, sorry. To be even more precise, we have heroically completed the two-phase culling refactor, sorry. And then we did some stuff that didn't help, and then we didn't do some stuff that we know wouldn't help. All right, so I think that's kind of all that I have the energy for today. I expected this to go different direction because I expected that we would actually be net positive on cluster culling at the end of the stream. But that clearly needs some investigation and thinking about the efficiency of the task shader invocations in this like sort of dummy way. And whether it is reasonable for us to do something else or not. Because we can do the perfectly optimal thing, it's a pain. So yeah, there is that. At this point, if we are doing per cluster work, actually, we probably have to do things a little differently. Yeah, essentially the high level has to change. and it's painful to change the high level. It's especially unfortunate because before this discovery, if you look at the pipeline that we have with or without mesh shading was an easy swap for a small portion of this pipeline. You have the pipeline, you keep the high level the same, and then you swap the lower level without changing the high level, and things work. So this was the very nice property of the code we used to have. And this is still a nice property of the code we have now, but cluster occlusion culling throws a wrench in this whole thing. And that is unfortunate because even if we can write the code that makes it more efficient, this now means that we are bifurcating the pipeline more so, which is just not a great feeling. But this is what it is. So far on AMD hardware, with our implementation, I want to keep stressing that we have to keep the occlusion culling for clusters disabled, even though it saves a lot of triangles to render, just because it's not net efficient. It's not net positive on efficiency. We might resolve this at some point. All right. That's kind of it. Any questions I missed on chat? XT shaders didn't work on NVIDIA. NVIDIA should have a driver that supports XT shaders. In fact, somebody on last stream was saying that they did run the code as is. There was a validation error, which we have right now as well, which is not critical, and it's a bug that is not in our code. Oh, sorry, let me double check that we didn't introduce validation problems, and then I can commit this code. So the code should work on NVIDIA without problems. Okay, we are all good. We have 4 validation errors because we are now the driver, the layers validate the code multiple times because we compile it twice now with 2 different specialization constant values. But none of these are our bugs. So it's the same problem that is a bug in GLSlang. So I think we're good. I can commit this code, or as in I can push the commits. I guess updated readme or something. And that's kind of where we will end. So yeah, so maybe you have to have a beta driver for mesh shading to work on NVIDIA. So that is it for now. Now I need to think about what to do with this problem, and also if mesh shading works at all on our GPU, which it should, but you never know. Then we might, so I'm guessing that probably the next stream is gonna be whenever I get the ARC GPU, and if it works with mesh shading, then we are gonna explore this exciting sort of path. And the biggest thing there I'm curious about is the efficiency considerations. A lot of the work that we had, not a lot of the work yet, but a lot of the problems, so like even the problem that we hit right now with the occlusion culling efficiency, is it AMD specific or not? It's hard to tell, because on one hand, fundamentally, we are doing something that's inefficient, which is to say we are submitting objects twice now through the task shade pipeline. So of course, it is reasonable to expect efficiency drop. At the same time, the efficiency drop should be limited to the task shader stage, because we are not submitting more meshlets. We are culling all of this away. And the way scaling works should make it all right, in the sense that every meshlet has 64 triangles, so there's 64x fewer triangles or meshlets than triangles. And so yes, we are increasing the amount of work. But the stage where we are doing that is the stage that is doing the least possible amount of work other than the draw call stuff. And also, well, no, I guess that's it, right? So like, you know, like this is kind of what it is. So is it still an efficiency problem on an Intel GPU to do what we are doing? We don't know. We'll have to test. Is it an efficiency problem on NVIDIA GPU? We don't know, we'll have to test. Depending on why the problem happens on an AMD GPU, the efficiency problem might be easier to recover or harder to recover, and the same is true of every other GPU as well. We can do the actual culling work ahead of time with very efficient sort of layout of work distribution. Is it gonna fix the problem? I don't know now. Because maybe the problem isn't we are doing the work. Maybe the problem is we are dispatching task shaders in general. Like it could be the case, so it takes, what, 4 milliseconds for 20,000 draw calls? Maybe reducing the amount of work on this driver that we are using in the shader doesn't change that at all. Like, it's hard to test. And the other thing I'm curious about is getting the mesh shaders to run on the official AMD driver, because maybe there something is different. But for that, I have to either build it from source or wait until they actually enable it. So anyway, I think the following stream will either be around Arc, or maybe I'll take some time to build the AMD open source driver and something's different there. Or maybe something else happens. I don't know. In either case, or I get some idea about what to do with this efficiency problem on the current setup. Either way, we are done for today. Thank you everyone who was attending. And there's the last question that I will answer. Is it possible to store ifdefs in SpirV? I'm trying to use GLSlang and SpirV-Cross to compile GLS shaders to metal and HLSL while maintaining the ifdefs. Yeah, not really. So the thing we did just now, this where was it? This guy, right? This guy. This is not an ifdef, but it's also not a runtime variable. It is somewhere in between. So these are called specialization constants. They are supported in Metal and Vulkan. I think the X12 doesn't support them yet, but I could be wrong on that. This is not quite an ifdef, because there are some things that this value can control and some things that it cannot control. For example, as of a recent update, I think it's Vulkan 1.3, you can here say, oh, I'm going to use a specialization constant to control this local size. I think the way you do this is something like this. I'm not going to attempt to actually go with this, but like, I think this should work. However, for example, this is 64. You can't say this because it becomes an expression and stuff, right? And you can't, and you can't say, oh, if late, then this, else something else, right? So there's a context, there's an expression context in which you can use this value. And the compiler will optimize this at runtime when you create the pipeline as if it was an ifdef. But the driver compiler. But there's cases where you can't use this value, right? So you can use specialization constants in SpirV. When you translate this to SpirV, to like GLSL or whatever, to any environment that doesn't support specialization constants, I don't know what exactly happens with SpirV-Cross, but I think in SpirV-Cross you should be able to specify the values of these guys so that it works for a fixed configuration. Or you can probably tell SpirV-Cross, even if you can't tell SpirV-Cross, it should be easy enough to convert these guys to basically keep we can actually, let's just see what happens. I've never done this before, but we now have, I should have SpirV-Cross here installed. It should have command line arguments for all of this. So let's just see. Let's pick the compute shader. So this guy has the specialization constant, which is called late, which is declared there. Let's see what happens when we just translate it. Right. So actually, if you convert this to GLSL with the specialization constant, as is without any extra arguments, it already compiles it to define, right? Because it essentially says whatever the value of this define is, if it's not there, default to false. Otherwise, use it. This means that if you use this GLSL shader and you prepend to this shader in the right place this define, setting this define to another value, then it will work, right? So SpirV-Cross is doing the right thing for specialization constants. However, this is the only thing that SpirV format supports as far as toggling behavior, and it can't toggle everything. So if specialization constants work for you, then the answer to your question is yes, you should use specialization constants in your source and then in your SpirV. And then SpirV-Cross should be able to translate this to whatever the reasonable equivalent of that is in your runtime. For example, I'm pretty sure that if you translate this to metal, then it should use metal's specialization shader. Let's see if this is true. Specialization constants. Dash MSL. Right, so oh boy, how do I, oh, this is wild. All right, so if you look at what happened in MSL, which is metal's shader, like shading language, then it converted this to a function constant. Function constant in MSL is the equivalent of specialization constant in Vulkan. And when you create a pipeline, you are supposed to specify the values for function constants in metal. And this is what you'll get, right? So SpirV-Cross looks like it's doing the correct thing for specialization constants. If you can use specialization constants over defines, I would recommend doing so. It is a better model for a bunch of reasons that maybe at some point I can talk about more. If whatever you want to do can't be expressed with specialization constants, then you're out of luck. You have to build several versions of SpirV blobs and then translate them separately, and then that's kind of just what it is, right? So yeah, that is that. All right, thank you everyone for attending. Watch Mastodon, Twitter, or whatever you watch for future installments of the series. As I said, it's probably going to be either Arc or a different AMD driver, or I learned some amazing thing about how to work around this problem that we are facing with efficiency of dummy task shaders. That is going to make me want to implement it, as opposed to the thing I'm feeling right now, which is, oh my God, you know, like why am I doing this? Like, it's a lot of pain to work around this problem. But if I get excited about the solution of this problem that feels promising, then maybe we'll do that instead, but we'll see. All right, thank you. See you guys next time, whenever that is.